faithfully convey value, interpreting great books from around the world. Hello, this is Sally's Book Talk. Today, the book we're going to interpret for you is The Moon. The book's subtitle is From Greek Mythology to the Modern Moon Landing, a complete record of human lunar exploration. How much do you know about lunar knowledge and legends? Feel free to share your thoughts in the comments section. The moon is the most prominent celestial body in the night sky and Earth's closest neighbor in the universe. Its average distance from Earth is about 384,000 kilometers. We can witness its radiance with the naked eye right here on Earth. The moon seems to possess an eternal and unique charm. From ancient times to the present, humanity's imagination and scientific exploration of the moon have never ceased. In 1969, the Apollo 11 spacecraft carried 3 astronauts to a successful moon landing, marking a giant leap in human lunar exploration history. Entering the 21st century, NASA announced plans to return to the moon, and China's Chang'e project is also in full swing. Countries worldwide have embraced a lunar exploration boom. Why is the moon so captivating? How has humanity's understanding of the moon evolved gradually over the long course of history? The Book of the Moon will give you the answers. The author, Bill Leatherbarrow, is former chairman of the lunar section of the British Astronomical Association, emeritus professor at the University of Sheffield, and a renowned science writer who has participated in creating and editing dozens of books. To honor his contributions to astronomical science popularization, the International Astronomical Union named asteroid 95,852 after him. Upon publication, the book received widespread acclaim and was recommended by BBC Sky at Night magazine and academic authorities. In the jointly recommended books by Choice magazine, it professionally explains the development of human lunar understanding, from classical to space age, records great moments in exploration, and provides comprehensive lunar knowledge. Next, I'll interpret the book's main content through 4 stages of human lunar understanding. First, classical era studies of the moon's motion patterns. Second, cartography-dominated lunar science during the telescope era. Third, the rise of lunar geological exploration. Fourth, analysis of lunar geology and origins during the space age. Let's begin by exploring classical era studies of the moon's motion patterns. Well, during this phase, lunar research shifted from religious superstition to science. The moon is the largest celestial body in the night sky, big enough for us on Earth to observe some surface details with just our naked eyes. Since the dawn of human civilization, people have observed the moon and raised all sorts of questions about this mysterious celestial body. What exactly is this round yellowish thing in the sky? How did it get up there? Why do we see phases like waxing and waning? Why does the moon move like this? What meaning and omens does the moon hold for humanity? What opportunities and dangers could the moon bring to humans? Well, for millennia, legends about the moon have been passed down across the world. The moon has also become a key symbol in human social, cultural, and religious beliefs. Greek mythology has tales of the moon goddess Selene, while Roman mythology tells stories of the moon goddess Luna. In China, we have stories like Chang'e flying to the moon and the heavenly dog devouring it. The moon is often seen as a cause for abnormal human behaviors, especially mental disorders, depicted in literature, art, and pop culture. For instance, in many films and shows, vampires and werewolves transform under the full moon. The ancients mostly explained lunar mysteries through superstition and myths. And, however, the ancients' moon observations weren't fruitless. They discovered regular phases and, based on its position, invented calendars, one of humanity's earliest ways to measure time and organize life. Yet, why did these regular changes happen? Our ancestors knew what occurred, but not why, still in that stage. To systematically understand phenomena like the moon's phases, solar eclipses, and lunar eclipses. Over 2 millennia ago, ancient Greek philosophers tried to ditch religious superstition and understand the moon's patterns in the night sky from an astronomical angle. The Greek mathematician Pythagoras observed and calculated that the moon is a sphere, doesn't emit its own light, and all its brightness comes from reflecting sunlight. The sun, which part of the moon we see, depends on which part is lit by sunlight. Due to oppression from Orthodox religious powers, astronomy developed very slowly. Orthodox Christian doctrine states that God created the world and humanity. Earth was the center of God's creation, with all celestial bodies revolving around it, until the European Renaissance, from the 14th to the 16th century, when astronomy made a major breakthrough. Among these, the most famous was the heliocentric theory proposed by astronomer Nicolaus Copernicus in the 16th century, which powerfully shattered the long-standing geocentric fallacy dominated by religion, achieving a fundamental transformation in astronomy. The heliocentric model was later refined by Kepler's laws of planetary motion and Newton's law of universal gravitation, gaining widespread acceptance and ultimately becoming a key foundation for modern cosmology. The heliocentric theory perfectly explains the moon's regular phases. It's all about the changing relative positions of Earth, moon, and sun, making the moon no longer mysterious. The moon's eternal face is because the time it takes to rotate once is the same as the time to orbit Earth once. So, from Earth we only see one fixed side, which puzzled our ancestors for ages. Solar and lunar eclipses were scientifically explained. The sun's diameter is 400 times the moon's, and the sun-Earth distance is exactly 400 times the moon-Earth distance. Thus, from Earth, the moon and sun look almost the same size. When the moon moves between the sun and Earth, it blocks sunlight, causing a solar eclipse. A lunar eclipse is just the opposite. Earth is between the sun and moon, blocking sunlight that would hit the moon, making it dark and forming a lunar eclipse. Since then, when people see solar or lunar eclipses, they no longer need to panic and beat drums to chase away the heavenly dog. As research into celestial motion laws deepened, more astronomical phenomena got scientifically explained. People finally realized those mysterious lunar phenomena were just natural results of celestial motions. Superstition and myths gradually gave way to astronomy based on physical laws. Though stripped of symbols and myths, for the distant moon, humans could only gaze from afar, unable to see its surface up close. Does it have mountains, rivers, and seas like Earth? It wasn't until humans invented the telescope and aimed it at the moon that we truly unveiled the mystery of the lunar surface's form. In Part 2, let's explore what progress was made in lunar science during the telescope era, dominated by cartography. The telescope was a major invention in scientific history, first created by Dutch spectacle maker Hans Lippershey in Middelburg in 1608. It used a tube with concave and convex lenses to see distant scenes clearly. This telescope quickly swept across Europe. Italian astronomer Galileo developed a strong interest in this new instrument and keenly recognized its profound impact on astronomy. In 1609, Galileo made his first telescope using one convex and one concave lens. It was about 4 centimeters in diameter, 1.2 meters long, with 20 times magnification, and he pointed it at the moon. After months of careful observation, Galileo drew numerous lunar images and wrote The Starry Messenger. This book documented his new discoveries through the telescope. The moon, through the telescope, revealed a rough surface with familiar terrains like mountains, canyons, plains, and seas, plus an uncommon feature: ubiquitous craters. Galileo also described a method to measure lunar mountain heights using shadow lengths and simple geometry. Human understanding of the moon reached new scientific heights. Galileo's findings caused a sensation, sparking widespread interest in observing the moon up close through telescopes. English explorer -- cartography Thomas Harriot invested heavily in a telescope, using it to create a more complete lunar map showing seas, craters, mountains, and even bright concentric ray structures. Harriot's lunar observations and mapping ignited a cartography craze that many continued. Thus, cartography dominated lunar science development. This was unsurprising as Europe was in an age of exploration and conquest, where maps held immense value for royalty and explorers. Map making and naming became symbolic ways to conquer and claim new worlds. Dutch cartographer Michael van Langren created over 30 precise images of different moon phases after long observation. In 1645, the first three-dimensional engraved lunar map, 34 centimeters in diameter, was produced from these precise images. This lunar engraved map was the first to systematically solve the naming challenges for numerous lunar surface features. He proposed 325 personal names for place names, turning the moon into a place to seek patronage and pay homage to the powerful. However, with unpredictable political shifts, this naming system didn't endure in history. With rapid advances in quality glass manufacturing, by the mid-17th century, people could produce larger telescopes with higher resolution. Polish brewer Johannes Hevelius built a rooftop observatory using a telescope with a 3.7-meter focal length to observe the moon. In 1647, he published a lunar map documenting his observations, including 3 complete lunar maps and 40 engravings of different moon phases, while supplementing and refining Langren's naming system with more lunar toponyms. Hevelius's lunar maps and engravings were remarkably accurate. For the next 150 years, they remained the reference standard for all lunar research. However, the naming systems of Langren and Hevelius didn't survive. Italian priest Giovanni Riccioli voiced objections to this naming system. In 1651, Riccioli published New Almagest, containing his lunar map and naming system. Instead of naming features after the privileged, he used common sense names describing weather, moods, and influences for large features, like the Sea of Rains and Sea of Tranquility. For smaller features, he used names of famous astronomers, scientists, and philosophers. Riccioli's system gained approval from Giovanni Cassini, director of Paris Observatory, who applied it in his lunar maps, helping it endure and become the foundation for nearly all subsequent lunar naming systems. So, from Isaac Newton's reflecting telescope in 1668 to the achromatic refractor's 18th century invention, telescope technology advanced significantly, enabling more accurate lunar observations. All line land force. In 1824, German cartographer Wilhelm Lohrmann published a truly modern lunar map, rich in surface details. Lohrmann also innovatively divided the moon into 25 regions, abandoning the holistic view and instead emphasizing details. It provided abundant close-ups, concentrating on meticulously mapping selected areas. This approach had a considerable influence on later generations. The pursuit of map-making precision grew increasingly higher, finally reaching its peak in 1837. That year, German astronomer Wilhelm Beer and geographer Johann Heinrich Mädler published an important work containing a map of the entire visible hemisphere of the moon, over 400 pages. Johann C.G. The map included rich details, precise measurements, and coordinates, along with descriptive explanations for each lunar feature. After that, people used more advanced telescopes for further lunar observation and research, but it was mostly minor refinements based on Beer and Mädler's outstanding achievements. And the reason I didn't find it out was that, as telescopes became larger and better, people observed more details on the lunar surface, and the lunar maps created by observers also grew larger. Despite many efforts to pursue extreme detail, people's understanding of the moon itself remains superficial. Why are there unique craters on the moon? How are features like Maria formed? Lunar cartography alone couldn't answer these questions. It wasn't until geological analysis was added in modern times that we achieved a major breakthrough in our lunar understanding. Next, let's explore humanity's investigation into the causes of lunar landforms during the geological era. After entering the 20th century, influenced by photography technology and the specialization of astronomy, humanity gained a clearer understanding of the moon. Photography was born in the 1830s, but early photographic technology was far from sensitive enough to capture faint or moving celestial bodies. Therefore, photography wasn't widely applied to celestial observation, and visual sketching remained mainstream. In the 1950s, photography technology advanced rapidly. In 1968 Innovation, planetary scientist Gerard Kuiper, then co-director of Yerkes Observatory and McDonald Observatory, applied photography to lunar research, quickly and efficiently obtaining a large number of high-resolution maps. He published the Lunar Photographic Atlas, containing 230 pages of images, which became the standard map before the space age and still holds important reference value today. And that is, Kuiper's more profound contribution to lunar research was promoting astronomy's professionalization, shifting lunar science leadership from amateurs to professional astronomers. Eisen calls.
In 1960, Kuiper founded the Lunar and Planetary Laboratory at the University of Arizona, opening a new chapter in human celestial research.
At the Lunar and Planetary Laboratory, Kuiper gathered and trained numerous astronomers, launching ambitious lunar programs that laid foundations for U.S. Air Force lunar aerospace maps and geological stratigraphy charts.
He also conducted systematic research on lunar craters.
A serendipitous discovery by staff member William Kenneth Hartman unveiled the mystery of lunar crater formation. Since the telescope era, humans have observed vast numbers of craters on the moon. So how were they formed? Scientists debated fiercely, with two main theories. Most lunar observers believed volcanic activity was the primary crater-forming mechanism. A minority argued for impact origins from asteroids and comets, championed by American Ralph B. Baldwin, an astrophysics graduate turned businessman. He devoted extensive spare time to studying the moon's unique crater structures. During War II, Baldwin specifically researched bomb blast craters. He argued lunar craters required immense explosive force, beyond volcanic processes like magma uplift, making impacts the only viable explanation. In 1948, Baldwin compiled his research into the book The Face of the Moon. In it, he analyzed vast crater data, firmly concluding lunar craters resulted from explosive impacts by massive meteorites striking at high speed. By comparing terrestrial blast craters, Baldwin divided lunar impacts into excavation and modification stages. In excavation, high-speed meteorites compress lunar rock, driving material downward and outward.
The shattering impact instantly releases a massive energy shockwave, forming the crater.
In modification, the shockwave propagates downward and rebounds, ejecting material to form the crater rim's peaks. Deep underground material is compressed and rebounds, forming concentric small craters. Baldwin's research didn't get enough attention or recognition, mainly because folks back then were too fixated on tiny details. What for small craters in limited views, it wasn't until 1961 when William Kenneth Hartman from the Lunar and Planetary Lab gave new evidence that the impact theory slowly got accepted. Hartman at the Lunar and Planetary Lab mainly worked on fixing images of the moon's edge areas. And moon photos from cameras are flat. How do we turn them back into a three-dimensional moon? Hartman projected multiple moon photos onto a white sphere about 90 centimeters across. Then he reshot the sphere from different angles to fix the blurry spots on the edges of the original photos. Oh, as Hartman walked around the sphere, he spotted several huge, gorgeous concentric craters.
The craters spanned kilometers. No volcanic activity could make something that big, so it had to be from impacts, solving the crater mystery.
Hartman's find gradually made the impact theory mainstream. Lunar geology took over from lunar mapping as the main research focus. But how can geology even work without exploration and analysis? This needs real close-up space-age probes to make moon visits possible. Next, let's learn about new mysteries uncovered by space probes visiting the moon. And since ancient times, humans noticed the moon spins and orbits in the same time. So we only see one side, making many wonder what the far side looks like. In 1959, the Soviet Luna 3 probe headed to lunar orbit and snapped the first pics of the moon's far side. This was a landmark, great achievement in human moon exploration history. The 29 photos from Luna 3 clearly showed the far side, geologically similar to the near side, but with big differences. It's covered in craters like the front, but has almost no low plains, called Maria. And the near sides, Maria, cover nearly 30% of the area. Why is there such a big difference? Luna 3 probe brought new puzzles. To find answers to these new puzzles, for half a century, countries have targeted the moon, conducting numerous exploration missions.
The Soviet Union and the U.S. raced to launch new probes, achieving lunar landings to collect loads of data and rock samples up close.
In 1969, the U.S. Apollo 11 spacecraft carried astronauts Armstrong, Aldrin, and Collins to successfully reach the moon, achieving humanity's first moon landing, a giant leap. After that, Europe, China, Japan, India, and other countries worldwide also launched extensive lunar exploration missions. Over half a century of the space age, humans have acquired vast amounts of photos. Rock sample survey data have unlocked tons of lunar mysteries, more than all human observations over millennia. Through geological research and data analysis of rock samples, geologists and astrophysicists found the moon has lower density than Earth, lacks water, has local magnetic fields, and uneven gravity distribution. Why do these characteristics exist? We need to look for answers in the moon's formation and geological evolution history. Regarding the moon's origin, humans have long proposed different hypotheses to solve this puzzle. Before the space age, humans could only keep proposing new theories and hypotheses, then rigorously test them scientifically to refute, discard, or update them. Among them, the most famous are the nebular hypothesis, the fission hypothesis, the capture hypothesis, and the giant impact hypothesis. The nebular hypothesis was proposed by German philosopher Kant in his 1755 book Universal Natural History, suggesting all solar system bodies evolved from primordial nebular material billions of years ago through gravitational and repulsive forces. The moon and Earth formed as a binary system condensing from the primordial nebula. The fission hypothesis was jointly proposed by British astronomer George Darwin and geologist Osmond Fisher in 1898. They believed the moon was once part of Earth, early in Earth's formation, when it was molten like magma. Rapid rotation's centrifugal force plus solar tides caused material to break away, forming today's moon. The capture hypothesis was jointly proposed by several American geologists in the early 19th century. This theory suggests that the moon formed elsewhere in the solar system and later migrated near Earth, where it was captured by Earth's gravity. This hypothesis isn't just a tall tale. In fact, many moons in the solar system were captured this way, like Triton, which was captured by Neptune's gravity. The giant impact hypothesis was proposed by American astronomers William Hartmann and Donald Davis in 1975. They believed that in the early solar system, when Earth wasn't fully formed and was molten, it collided violently with a Mars-sized protoplanet called Theia. Theia was shattered and melted, ejecting material from Earth. This debris scattered around Earth and coalesced through gravity to form the moon. Space-age probes gathered vast data and rock samples, helping us better understand the moon's origin. Through compositional analysis of rock samples, scientists found significant differences in elements between the moon and Earth, disproving the nebular and fission hypotheses. Olive, sound. Modern supercomputer simulations show the moon's size and mass are much larger than typical moons in the solar system. The conditions needed for lunar capture by Earth's gravity are extremely rare and almost impossible.
Thus, the giant impact hypothesis is now the most widely accepted theory, reasonably explaining the moon's features.
The giant impact hypothesis states that after Earth collided with Theia, only lighter materials were ejected, and this debris coalesced to form the moon. This explains why the moon's density is significantly lower than Earth's. The newly formed moon was extremely hot, driving off volatile components. This accounts for the minimal water in Apollo rock samples. The moon's small size and mass allowed rapid cooling. During debris accumulation, metallic material cooled rapidly in localized areas, forming magnetic fields. The uneven distribution of this metallic material caused the moon's gravitational anomalies. Analyzing rock samples also helps us understand the moon's geological evolution. Analysis of lunar rock composition confirms Baldwin's impact origin theory from the geological era. The impact theory states that massive meteorite strikes shaped the moon's basins in craters. But volcanic theory supporters needn't feel completely defeated. Probes have found volcanic evidence too. Through volcanic activity, the moon developed minor geological features like rills, concentric patterns, and wrinkles similar to Earth's. Human lunar understanding didn't happen overnight. It evolved gradually through history. In the classical era, we freed the moon from religious superstition. The telescope era brought scientific observation and mapping, accumulating rich cartographic data. The geological era introduced new perspectives and theories that brought us closer to the moon's essence. Space-age probes returned vast data and samples, enabling comprehensive lunar understanding. As we unveil the moon's mysteries layer by layer, new questions emerge. Many puzzles still await exploration. For instance, why the far side has more craters remains unresolved. The moon's charm only grows. What future surprises might it hold? What are your visions for lunar development? Feel free to share your thoughts in the comment section. That concludes our interpretation of the Book of the Moon. Listening notes are below the audio. See you next time.